Signals and Systems Laplace Transforms Part 1 Series on Signals and Systems Lecture number 4.11. Laplace transforms, like Fourier transforms, they are used to convert a time domain signal into frequency domain and vice versa. However, these transforms, Laplace transforms, exhibit certain differences when compared with Fourier transforms. In Fourier transforms, the transform variable is real frequency, whereas in Laplace transforms, the transform variable is a complex quantity. Yes. Another difference is Fourier transforms, they are well suited and they are widely used in the analysis of signals, whereas Laplace transforms, they are widely used and they are also best suited for the analysis of systems. Another difference is Laplace transforms. They take into account the losses that takes place while system is in operation, whereas Fourier transforms assume lossless or loss-free conditions when they are used in the analysis of signals or systems. With this small introduction, now let us move further. As the session is long, it is split into two. In the first one, the focus is on definition, existence, convergence, and some properties of Laplace transforms. This is first one, to study and understand Laplace transforms. We begin with the definition of Laplace transform. There are two types of Laplace transforms. One is bilateral, another is unilateral. Before going to the definition of bilateral and unilateral transforms, let us have a small introductory and key points useful in understanding the nature of transforms. Laplace transforms are useful to transform integral convolutions and differential equations into algebraic equations. Notice, algebraic equations are always easy to deal with or to manipulate when compared to integral or differential equations. So, Laplace transforms, they have the ability of reducing the level of complexity, the level of difficulty while analyzing systems as well as signals. It is a more general form. Laplace transform is a more general form, and Fourier transform is just a special case obtained by letting S equal to j omega. S stands for complex frequency. It's a relation with the real frequency is S equal to sigma plus j omega. Omega is real frequency, sigma is a constant that represents attenuation. J is there, therefore S is complex quantity. When sigma, which represents attenuation, when it becomes 0, S becomes j omega. In such case, Laplace transform becomes Fourier transform. As already mentioned, there are two types of transforms, bilateral and unilateral. Before going further, it is to be mentioned that bilateral is hardly used, whereas unilateral transform is the one that is widely used. And when Laplace transform is mentioned, it implies that it is unilateral transform. Bilateral transform is also known as two-sided transform. Unilateral one is also known as one-sided transform. Now bilateral. F of S is equal to integral minus infinity to plus infinity f of t e power minus st dt. This is bilateral Laplace transform of a time domain signal f of t. Unilateral transform is very much similar to bilateral transform, except small difference, that is lower limit on the integral sign. In bilateral transform, lower limit is minus infinity. In unilateral, it is 0 minus. And these two are forward transforms. They convert time domain signal into frequency domain. Reverse transform is given here as a third relation in this slide. F of t is equal to 1 by 2 pi j integral sigma minus j infinity to sigma plus j infinity f of s e power st ds. Before going further, just it requires to be mentioned that transform variable in case of Laplace transforms is yes. It is called complex frequency. As already mentioned, it is equal to sigma plus j omega. Some more points regarding transforms, Laplace transform. For a bilateral transform, the inverse transform of a function f of s. F of s is bilateral transform of f of t. This particular point says inverse transform of a function f of s, that is f of t, is not unique unless a region of convergence ROC is specified. So there is an ambiguity in the inverse transform if ROC is not specified. ROC stands for region of convergence. It is a region on S plane. This region consists of values of S for which transform exists. Here it is being mentioned that in bilateral transform there is an ambiguity unless of course ROC is specified. In case of unilateral transform, all functions exist only for positive values of t and 0 for negative values of t. Hence, there is no ambiguity in the inverse transform even when ROC is not given. So inverse transform is unique in case of unilateral. Bilateral is associated with ambiguity. Unilateral is associated with no ambiguity. In case of bilateral, ambiguity can be eliminated by mentioning ROC. These are the 3 points, key points as far as this slide is concerned. Now, existence and convergence. A few points regarding the existence of transform, Laplace transform. The Laplace transform to exist one-sided. Integral 0 to infinity f of t e power minus st dt, it must be finite. Then only f of s, this is equal to f of s. F of s becomes finite. So for f of s to exist, the integral 0 to infinity magnitude or modulus or absolute value of f of t e power minus sigma t dt should be less than infinity, means finite. This integral should be finite. This is the condition for existence. The Laplace transform converges for values of s given by real s, that is equal to sigma more than alpha, where alpha is a real positive number satisfying the condition. Limit t tends to infinity e power minus alpha t f of t equal to 0. So in this slide, there are two statements. First statement pertains to existence. Second statement pertains to convergence. In general, given a signal, one of the following may happen. 4 points are given in this slide. All these points belong to existence and convergence of Laplace transforms. The signal's Laplace transform may not exist. In other words, there is no ROC. The functions e power t square and e power t are such examples. The Laplace transform may exist and is an irrational function of S. Third possibility is Laplace transform exists but cannot be expressed in closed form. Most signals encountered in practice belong to this type. Laplace transform exists and is a rational function of S. So in general, one of the 4 situations exists. Now we spend some time on properties of Laplace transforms. Linearity. Linearity property can be stated mathematically as Laplace transform of a signal consisting of sum of 2 signals. What are those 2 signals? A, x of t, B, y of t. A is constant, B is constant, x is one signal, y is another signal. Laplace transform of this signal, which is combination of 2 signals, or weighted combination of 2 signals, it is equal to A x of s plus B y of s. Notice here it is same A, which is weighting function x of t. Here it is the same B, which is weighting function y of t in time domain. So weighting remains same. X of s is Laplace transform of x of t, y of s is Laplace transform of y of t. Linearity property can be simply stated as superposition principle. If a system or signal or transform obeys superposition, then it is linear. We talk about linearity later in another session. Another property obeyed by Laplace transforms is scaling. Here it is a time scaling. This property can be stated as Laplace transform of f of a t is equal to 1 by a f of s by a. Here a is positive. In case of bilateral transform, scaling property can be stated as Laplace transform of f of a t is equal to 1 by mod a f of s by a. So this is scaling property. Then we move to time shifting property. Laplace transform of f of t minus t naught is f of s multiplied by e power minus s t naught. Here t naught is positive. When it is positive, f of t minus t naught is delayed version of f of t. So this is a case of time delay. Now we consider the case of time advance. Laplace transform of f of t plus t naught is equal to e power s t naught multiplied by f of s minus integral 0 to t naught f of t e power minus st dt. Here t naught is positive. As already mentioned, it is plus t naught. So it is advance, time advance. Now we consider frequency shifting property. According to this property, Laplace transform of f of t e power s naught to t is f of s minus s naught. Notice shifting in frequency domain, it corresponds to multiplication with exponential in time domain. Now we consider time differentiation. Laplace transform of nth differential of f of t is equal to s power n f of s minus s power n minus 1 f of 0 minus s power n minus 2 f1 0 minus etc. Ultimately f of n minus 1 0 minus. From this, when differentiation is once, that is df by dt, Laplace transform of df by dt is equal to s f of s minus f of small f of 0 minus. Now we consider frequency differentiation. Regarding time differentiation, one point can be mentioned. Differentiation in time domain corresponds to multiplication by s power n in frequency domain. General, not specifically. Differentiation n times in time domain means multiplication with s power n in frequency domain. Now we come to frequency differentiation. Laplace transform of minus t f of t is df by ds. So one can notice that differentiation in frequency domain corresponds to multiplication in time domain with t. Time integration. Laplace transform of integral minus infinity to t f of tau d tau is f of s by s plus f minus 1 0 minus 1 by s. One can notice integration in time domain corresponds to division by s in frequency domain. Notice differentiation in time domain corresponds to multiplication with s. Integration corresponds to division with s. Now we consider frequency integration, frequency domain integration. Laplace transform of f of t by t is integral s to infinity f of s ds. Here integration is in frequency domain and time domain signal is getting divided by t. So integration in frequency domain corresponds to division by t in time domain. Time convolution. Laplace transform of f1 convolving with f2. It is f1s multiplied by f2s. It means convolution in time domain corresponds to multiplication in frequency domain. Now frequency convolution theorem. Laplace transform of product of two functions f1 and f2 is 1 by 2 pi j multiplied by f1 convolution with f2. So one can notice convolution in frequency domain corresponds to multiplication in time domain. With this, we come to an end to the first part of this session. In this part, we covered definition, existence, convergence, and properties. In the second part, we cover some more aspects of the Laplace transform. We meet again soon in the second part.